We're going to start talking about something called Christophil's algorithm. Always forget it's with a F. We're going to get, I should be honest, it's really going to get extremely close to the full execution of Christophil's algorithm. What we're going to do is we're going to use most of the design elements to achieve the outcome that the book has with their branch and bound algorithm. This is just a little bit more straightforward of a process. It also gives us a chance to highlight a bunch of other algorithms that we've developed and put them together into like a cohesive strategy. Okay, so keep in mind, if you look up Christophil's algorithm, it's going to do a little better because there's a little more involved. Basically, there's a sorting algorithm in the end. And I'll point out where you can achieve better results than what we're going to guarantee. All right, so the first thing to keep in mind is this is an attempt. Let me say address, because the word solve would be a pretty bad word for this. Attempt to address the traveling salesman problem. Okay. And traveling salesman problems, it's annoying to write that over and over again. So these are usually referred to as TSPs. All right, so let me take a quick moment here to explain what a traveling salesman problem is. So essentially what you have is you have n vertices. The kind of two perspectives on this. Could be looking at it from a complete perspective, which is typically what is done, even if that's not where you are. I'll explain that a little bit. Or it's just they're all connected together. Right, in some subgraph of the complete graph, Kn, right? All right, now, typically the reason why this seems to be like this is all fuzzed together is that if they're all connected together, the way you approach this problem is you just think about the completion of the graph. So for instance, if you had to go from San Francisco to New York, you don't get particularly upset if the best way to do that is to stop at two cities along the way, right? Whether you're driving or flying or whatever. You just take that as part of the most efficient way to get from one point to the other. And so that you kind of interpret it as you can get from any one place to any other place. So that's why it seems like it always seems to look like we're talking about complete graphs. And then when you go to do a practical problem, not everything is directly connected, but there are routes, and we can represent that as a direct connection just with a route. To do that. Okay, so a traveling salesman problem is just the most efficient way to visit n vertices in either a Hamilton circuit properly, or if it's done and you kind of get worried about this, it's a Hamilton circuit on the completion. So we'll see what that looks like after a little bit. Right, and just imagine being a UPS driver, right? If you have to drive by someone's house because that's just part of how the roads are designed, you don't just give up on the problem. You still are solving a traveling salesman problem. Okay, so it's about finding Hamilton circuits, either the cheapest or one of the cheapest Hamilton circuits. And what you'd say would be a solution to the traveling salesman problem is to literally find one of the cheapest, right? If there's a tie, or the cheapest, if there isn't. Now, I have to say to address the traveling salesman problem, because in practice, this is incredibly expensive, right? So, take for instance, okay, 50. This is a good size because you can think about the 50 states of the U.S., or you can pick your 50 favorite cities, or you could, I don't know, if you find there's 50 McDonald's you want to visit, I don't know, whatever you want to do, just take 50 of them and think, okay, what's the best way to visit all 50? And again, I'm going through this for those that aren't familiar with these, so that it's possible if you already know a ton about traveling salesman problems, this is just worth skipping ahead. But if you think about this, what you have to do is to solve this properly, the first thing you would go to is a brute force algorithm. And so you would just list all routes and cost. Right, so you also have to calculate the cost, and you just pick the cheapest. That would be the brute force method. Right, if your number of nodes is relatively small, like 7 or 12 or 10, you could do this in an Excel spreadsheet. I'm not entirely sure where that boundary would be, but it comes down to what you can pull off your software. But when you're doing 50, what you should look at is 50 factorial. And this is way back on another page of my notes, but I do have it. So I try to update this all the time, but I updated this fairly recently. And let's suppose it just takes one calculation per route, right? That's a gross understatement. So it's definitely way worse than what I have here. But let's say one calculation per route is the expense of brute forcing this. All right, now of course we don't want to do this humanly because it's going to take a long amount of time. So maybe let's take the biggest supercomputer, the fastest supercomputer we can find, which fairly recently I looked up was the Summit 2021. It might be one to look this up that was coming online. We'll have to see. Check it out. It does 1 exaflop. And this is floating point operations per second. Or 1 exaflops. I'm not sure if it's really plural. I think people just say 1 exaflop. And this is actually 1,000 petaflops. That's relevant. Usually in the past it was petaflops that supercomputers were measured in, at least when they were this fast. If you want to know, right, that's 1 times 10 to the 18 floating point. So basically 1 times 10 to the 18 operations per second. Okay, so you can think of it as 1 calculation per second. So if you want to know how long it would take to do 50 factorial of these, all you have to do is do a division problem. And this is way more fun in class because then I get to set you all loose to take guesses or try to figure this out. But what this turns out to be is still a lot of seconds. I have in my notes 3 times 10 to the 46 seconds. Which, if your brain is clicking, this is pretty bad news because this is about 9 times 10 to the 38 years. Check out the theoretical age of the universe, and you'll find this is way beyond that. Okay, so we have a problem that's not very large, 50 nodes, right? You could imagine also ordering 50 different things from warehouse, and a warehouse worker has to go and pick these 50 things. Something part-time job I had a long time ago. Right, there's lots of problems of this scale, and yet the idea of actually knowing that you have the best solution is out of reach. Okay, so this is why I'm careful, at least at this moment, to say address the traveling salesman problem. Because if we can't brute force it, we're going to have to try something else. And what we do is we design an algorithm that will at least give us certain amounts of cost that we can guarantee. What we're going to be able to do is we're going to relate the sort of the worst case cost that we can generate. We can definitely give a route to the minimal spanning tree of a graph. All right, so we'll continue, of course, on this, but let me see if I can summarize for you a little bit. So we're not going to ever be able to solve the traveling salesman problem for reasonably sized problems, and I mean this in this sense, right? You don't need thousands of nodes or massive traveling salesman problems. These things grow out of control very quickly. I think even like 40-some factorial is still quite bad. And you can actually do this yourself, right? Suppose you're willing to dedicate a year to solving a traveling salesman problem. See how many nodes this particular supercomputer can handle. All you gotta do is just keep adjusting that 50 factorial down until it's about a year or whatever time frame you allow. Okay, so the thing is, you're interested in designing routes that aren't super expensive And the best way that this is done is typically with minimal spanning trees and then some embellishment from there. All right, and that's what we're going to do. So our first step is going to be minimal spanning trees in this algorithm design. Before we get there though, we do need to talk about a geometric property the graphs either need to have or repairs we need to make to the graph so that we're aware of how the algorithm needs to work if those properties aren't met. Okay, so I'll see y'all on the next one.